Next up, we have Shayak from Peloton talking about timely personalization at Peloton, a system and algorithm for boosting time-relevant content.
Thank you, Justin. Okay, and now I know which way to go. Sorry about that. Technology is very challenging, as some of you already may know. In fact, that's why I brought myself technology-proof speaker notes. My name is Shayak Banerjee. I work at a company called Peloton, which some of you may have heard of. And today we'll be talking about timely personalization at Peloton. We look at why it's necessary to personalize Peloton, why that personalization needs to be timely in nature, and how we built a system and algorithms to achieve boosting of time-relevant content. I have some wonderful co-authors on this paper, some of whom are here in this audience today. So what is Peloton and why do we personalize it? So Peloton is a platform for fitness content. We have instructor-led classes. We have tens of thousands of classes. Some of them are instructor-led. There are classes in cycling, running, outdoor running, yoga, basically any fitness discipline you can think of. There's also like a whole library of non-instructor-led content. So you can do things like scenic rides, scenic runs. You can even play games. So you can use your bike or tread as a controller and get your workout while playing a game. So we have this ever-expanding library. We have 7 million users as of May 2022. And we have a diversity of needs on the user side and a diversity of classes. So that brings about the need to personalize the content discovery experience. I just want to put in one word to say personalizing fitness is not purely personalizing the content, right? There are other layers at which you can personalize. Like if you are working out every week, we can personalize an entire schedule for you. While you're taking a single class, we can think about personalizing your targets within that class. So if we think you're a very fit user, maybe we ask you to hit 12 reps instead of 10 reps for an exercise. But today we'll be focusing on the personalization of the content discovery experience. And in particular, we'll be looking at how we balance engagement with other competing business goals. One of these business goals that we often are faced with is surfacing timely content. So we have a very dynamic inventory. Classes are constantly being added, and some of these classes are along certain themes. What are good examples, right? So one here on the top right, you'll see our one of our famous instructors, Robin Arzon. She's doing a 30-minute Momento Latino ride. It's specifically filmed for Latinx Heritage Month. And so in recommendations, we kind of have to surface this between September 15th and October 15th. It cannot be surfaced outside of this time window, right? Another example is sometimes artists like Beyonce and Eminem will do a partnership with Peloton. They'll say, okay, we'll allow you to film a series of classes uniquely based on our music. And now, in order for this partnership to be financially feasible to both sides, we have to take those set of classes and surface it to a large audience within a short span of time. So we call this surfacing of timely content as boosting. And I just want to spend a second differentiating this from promotions. So in our terminology, promotions is when you want to surface the same thing to everyone, regardless of their tastes or preferences. But boosting is a little more nuanced than that, where we use our recommender models to increase the target audience for a set of classes while still respecting their tastes and preferences. In many ways, this is actually similar to news recommendation problems, where certain articles are probably only relevant within a short time span, and you have to surface it to a large audience. So the first thing is we sat down with our stakeholders. They're in the content creation team, in the music team, in the marketing team, and we said, okay, what do you want from a system that helps give you some control over our recommendations? And at the end of the day, this is kind of the system that we came up with. And you'll see that the only thing that our partners have to enter is an entry in our content management system, which has 4 inputs. The boost parameters help us figure out, okay, which is the set of classes you actually want to target. There's a start date and an end date. We do not want our stakeholders to boost things for infinite durations of time, and we greatly encourage them to narrow the time windows for boosting. And we specify a boost value. And so this is the critical one to understand, because the agreement with our stakeholders here is that if you specify a boost value, typically between 1 and 5, whatever that number is, we will use that as a multiplier to increase the number of impressions. So if you enter 2 and a particular set of classes was going to get 1,000 impressions, we'll try to guarantee that that set of classes gets 2,000 impressions instead. So once we have this, basically we will pick that up. We'll run a daily job, which will pre-compute the boost values for the entire library of classes. And we'll make this data available to our batch pipelines as well as our online recommendations. So we do have both batch and real-time recommendation use cases. What we do in the batch world is we get predictions from our model, which is running on GPU using neural networks. Matthias will be happy to know that it is using huge CTR. We do some re-ranking based on the boost values, and then we generate the recommendations. We do something very similar in the online world, where we'll do the same re-ranking using the boost values right after candidate generation and model scoring. And in the online world, we'll typically have to store these boost values in some online key value store like Redis to have easy access. So one question you could ask is, okay, I see the system, but what's the algorithm, right? Now, when we were starting off with this, I think our main focus was, let's get this working end-to-end, right? And use the simplest algorithm possible. And so we landed on multiplicative boosting. The name might sound fancy, but as you can imagine, it's very simple. We take the score that's coming out of the model, the prediction score, multiply it by the boost value, and then re-rank and deliver the top K. That's the simple algorithm to apply boosting. Why does this make sense? So if you think about a user's ranked list of predictions and you're taking a cut of top K, there might be some content or some classes they were interested in which were marginally outside that top K. But now that you're doing this multiplication, it forces those classes into the top K list. Whereas if something is very far down, very low score, it will still not make it into the top K list. So intuitively, it made sense for us to lead with this. And of course, it turned out to be easy to implement, both online and offline. It helped us set up our systems to run end-to-end. But then we ran some A/B tests, right? And this is what we observed. So we ran 3 experiments applying different boosts. You can see there were some target impressions lift, and we measured the actual lift in impressions. You can see in all of those cases, we kind of blew past our targets, right? 3x led to 30x. Another 3x target led to 111x. That in itself is not as concerning as the fact that this was causing a change in user engagement. So what we are seeing is the conversion from our recommendations was actually dropping. You can see a 9% drop and 11% drop. So what does that mean? That means we were effectively surfacing these classes to users who didn't have much interest in them, right? So then we started thinking about, okay, how can we do better than multiplicative boost, right? One observation we had is most of our recommendations today are generated in batch. They're pre-computed, they're served up to the user when they log in. So in batch, we are generating everyone's recommendations at the same time. So it's actually very easy to estimate impressions in that scenario. And I won't go very deep into the math, but you can calculate impressions as long as you know your selection algorithm for recommendations. Our selection algorithm is very simple. You just take the top K and then do a weighted random choice in there. So given that, it's easy to estimate the impressions for the classes that you're interested in boosting, right? So now the challenge is, how can we get boost times this number of impressions while preserving engagement? And so we formulated this as an optimization problem. There is a selection variable, a sub nm, which is a binary variable, which is basically telling us which of the classes should we actually select for the user's top K list. We have a boost variable, b sub nm, which is telling us what boost value do we apply to each selection. And this is kind of the formulation. Again, details are in the paper. But what it is trying to do is it's trying to maximize the sum of predicted scores for the selected classes. That's our proxy for preserving engagement. And the primary constraint there is trying to ensure the number of impressions generated is greater than the desired target. So you will notice about this formulation is that it's a binary integer programming problem. It's NP hard. We needed some approximations to solve this problem. But before I go into that, here's a quick illustration of how this would work in practice. So imagine you have three users, U1, U2, and U3. We have a top K list, and K is equal to 2. So In gray, you see the selected classes for U1, U2, and U3. Let's say we have 2 classes we want to boost, C3 and C4. Right now, you'll see only C4 actually shows up in anyone's top K list. And the probability of surfacing that is basically that prediction score, 0.4 divided by the sum of the scores across that user. So it's a third. Now let's say you want a boost value of 3. You want to get an aggregate 1 impression, right? After running through optimization, this is what the solution might look like. So pretty much the same selections as before, except for user 3, we've now picked one item which is outside that top K, right? And we've given it a boost value of 3. And so now what's happened is if you look at the aggregate number of impressions, you'll see that for user 2, you have 0.5 probability of surfacing a boosted class, same for user 3, and that gives you an aggregate of 1 impression. So approximations, right? I'm an engineer. I need to get this actually working in production. So we had to approximate to simplify this problem. The biggest realization we had was that this entire top K thresholding is kind of a hard limitation, and it actually leads to a lot of non-linearities in the problem. So how can we achieve a top K effect without actually this hard threshold? Well, one thing we realized is let's take the scores and multiply them by this soft top K function, right? Here's the shape of the function on the top right for different values of a tunable parameter. And in the graph below that, you'll see that when you multiply the prediction scores by that, what you're doing is ensuring that the scores decay after the kth position. So that means when you do a weighted random selection on the entire list, you're no longer taking a cut of top K, you're taking the entire list. The classes outside the top K have a very low chance of actually coming in, right? So that's one simplification. Once we apply that simplification, it turns out that you can completely simplify the optimization formulation. So the constraint now becomes only dependent on the boost values. And the objective now becomes, let's minimize the boost values for these individual classes, because that should translate to the highest sum of the prediction scores. So we took this one step further. We took that objective, took the constraint, squashed them together in a cost function with another tunable parameter. And we can, so the first term there is basically saying, let's ensure we meet our lift in impressions, and the second term is saying let's minimize the amount of boost. The gradient of this cost function is analytically derivable, which is amazing because now we can solve this using gradient descent. And gradient descent is scalable. It can scale to hundreds of, we apply gradient descent using Spark. We can scale this to hundreds of millions of users and hundreds of thousands of classes. So let's call this algorithmic boost. We ran some ABC tests to see how this performs against multiplicative boosts. 2 experiments here. What you will notice is that we had 3 arms here. We had control with no boosts, we had multiplicative boosts, and we had algorithmic boosts. What you will notice is that in terms of the conversion rate, algorithmic boost did much better. So where we were observing an 18% drop with multiplicative boost, we had no drop. But this algorithm is now struggling to actually meet the target number of impressions. So where we wanted 2x, it actually led to 1.4x, and in the second experiment, results are kind of similar. So in summary, we have a recommender system at Peloton. We're trying to balance needs of the business with the needs of the user. We showed you we have content that's timely in nature. We have to surface it within a short time period. We've created a system that we allow our stakeholders to use in order for them to have some control over recommendations. We've shown you 2 different algorithms that we tried, multiplicative boosting and algorithmic boosting. A couple of things about what's next for us. One is that for the purpose of this experiment, these experiments, I was able to hand tune the algorithm, but there are still some operational concerns where for boosts of different sizes, this job still needs some manual effort. So that's definitely on our radar. But now that we've given this tool to our users, they are using it, and they are surfacing needs on a weekly basis. They want to target specific experiences. They want to target specific audiences in specific countries, right? Like they want to boost Spice Girls in the UK only. So how do we open up this system even more to give them that control? And lastly, I guess the big problem on our mind is we did this in batch, right? It worked beautifully in batch because we generate everyone's recommendations at the same time. But what happens when we generate recommendations as the user logs in? How can we do boosting during that time? That is all. Thank you very much.
Oh, it looks like we're just out of time. There are a bunch of questions online, though, if you want to kind of follow up on them.
Absolutely.
Yeah,
Thank you very much.
thanks.